There's a really strange feeling you get walking through a huge modern industrial site like the ABM Project.
Hmm.
You're surrounded by, the absolute bleeding edge of technology. You've got digital relays, automated systems, these massive substations just humming with power. It feels like science fiction.
It really does.
And then you look on the wall and you see a tool that looks like it belongs in a museum.
It's jarring, isn't it?
Yeah,
You're looking at these high-voltage transformers that could power a small town, and right next to them is, well, it looks like a shepherd's crook.
exactly. A literal stick with a hook on the end. But that stick is what we're talking about today, and it's probably the most sophisticated piece of life-saving engineering on that wall when things go terribly wrong.
We're talking about the rescue hook.
We are, and honestly, digging into the ABM training documents, this simple-looking tool is often the only thing standing between a really bad day and a funeral.
And the stakes for this deep dive are they're incredibly high. We're working from the official electrical safety training program for the ABM Project site. This isn't some generic brochure.
Yeah.
This is the tactical plan for an absolute worst-case scenario. We're talking about the can't-release phenomenon.
Let's define that right away, because can't release sounds a little technical, but the reality is it's horrifying.
It's tetany.
Right, exactly. Tetany, it's a physiological reaction where the electrical current just hijacks your entire nervous system.
It overrides your own body's signals.
Completely. If you grab an energized wire or maybe touch a live cabinet, the current forces your muscles to contract violently, involuntarily. Your hand clamps shut. You physically cannot let go.
That is the nightmare scenario for anyone in the electrical field. It's not a choice. You're locked on. And that's why this tool exists.
Precisely.
So today we're going to unpack the physics of this hook, the psychology of the rescue, and the very specific protocols ABM has. Because if you are reaching for this tool, you are already in the middle of a life or death crisis. Yeah, the goal here is to bridge that gap between just seeing the hook on the wall and actually having the mental software to use it. Because in that moment, panic is your absolute worst enemy.
Okay, so let's start with the hardware itself. Know your weapon, so to speak. The manual calls it a non-conductive pole device.
Right.
Which sounds simple, but looking at the specs for ABM, there's a lot more going on than just a plastic stick.
Oh, absolutely. If you grab, say, a random wooden broom handle to pull someone off a circuit, you might just die right there with them.
Because wood can be conductive.
Wood can hold moisture, and at high voltages, that moisture becomes a highway for electricity. The ABM rescue hooks are engineered for dielectric strength. They're usually a specialized fiberglass composite, sometimes with a foam core, all designed to repel electricity.
And the number that really jumps out is 50 kV. The manual is explicit that these hooks are rated for 50,000 volts. That's a huge amount of protection.
It's the critical spec. I mean, think about what that really represents. You're holding the handle. A few feet away, the hook is touching a person who's energized with thousands of volts.
Yeah.
That fiberglass pole is the only insulator stopping that current from traveling up the tool, across your own heart, and into the ground.
Yeah.
It's a firewall for electricity.
The manual also mentions the length, typically 4 to 8 feet long. I'm guessing that length is a very deliberate trade-off.
It is, yeah. It's a balance. You want enough distance to stay out of the arc flash zone,
Yeah.
but you also need enough leverage to actually move a person.
And ABM lists a few different types. You've got the standard J-hook.
Which is exactly what it sounds like, yeah.
And then there's the shepherd's crook, which we mentioned. That shape can't just be for tradition, right? Is there a functional difference?
There's a huge functional difference.
Yeah.
It's all about capture. The shepherd's crook has that deeper, looped design. It's not just for pulling. It lets you get a more secure grip on a limb, or even around the torso. If you're trying to move a 200-pound person who is just dead weight.
Right. No muscle tone helping you at all.
Exactly. That extra curve helps prevent them from slipping off the hook mid-pull.
That makes a ton of sense. The last thing you want is to get them halfway clear and then lose your grip. The documents also mention a telescoping hook.
They do.
That sounds useful, but does it introduce a weak point?
It can, yeah. The benefit is obvious storage, adjustable reach. If you're in a cramped switchgear room, an 8-foot fixed pole is a nightmare to handle.
You could hit something else that's live.
Right. The telescoping hook lets you adjust. But, and this is a big but, you have to be absolutely sure those locking mechanisms are engaged. You do not want that pole collapsing on you while you're pulling with all your might.
So no matter the shape J-hook, shepherd, telescoping, the core idea is the same. Reach plus insulation equals survival.
That's the formula. You're trying to move a heavy, energized object without becoming part of the circuit yourself.
Which brings us to, I think, the most dangerous part of this whole thing. The human element.
Hmm.
The ABM training has this section, Emergency Response Priority. And reading it, my gut instinct is completely wrong. And I bet most people's would be.
I think that's true for 99% of us. We're wired to help. You see a colleague, maybe a friend, shaking against an electrical panel. Your brain just screams, grab them.
The hero instinct.
Exactly. But in this one specific situation, that instinct is a trap. It's a fatal flaw.
Empathy without protocol is fatal.
That's it. If you touch them, you become them. The current doesn't care if you're a hero. It just sees another path to ground. That's why the second victim statistics are so tragic in these accidents.
So let's walk through the ABM protocol. This sequence is designed to override that instinct. Step 1 is alert.
Right. Call for help. Hit the emergency button. It feels so counterintuitive because every second feels like an hour.
But you can't handle this alone.
You can't. You need medics on the way. You need backup. You can't be a hero in silence.
Okay, step 2, assess. And this isn't just looking at the victim. The manual implies a tactical scan of the whole area.
You have to read the room in a split second. Is there water on the floor? Is there smoke? If you run in and slip, you fall into the equipment. Now you have 2 victims. You have to secure your own position first.
Then step 3, de-energize. This is the one that really stood out. The best rescue hook is actually a switch.
100%. The safest rescue is a de-energized one. If you know where that emergency stop or the breaker is, you hit that first. Killing the power is always plan A. The hook is plan B.
That is a critical distinction. You only reach for the hook if you cannot cut the power.
Right. Maybe the switch is blocked or it's locked out or you just don't know which one it is. That, and only that, is when you move to step 4, rescue.
And step 5, provide aid, only happens after all of that.
Correct. You can't do CPR on someone who is still conducting electricity. You have to get them clear of the hazard first.
It's a brutal, cold logic, isn't it?
It's triage logic. It ensures there's one survivor left to perform CPR instead of 2 bodies.
Okay, let's zoom in on step 4, the rescue. The switch is out of reach. We've got the hook in our hands. The ABM manual gets very, very specific on technique here.
Yeah, it's not a carnival game. And it starts before you even point the pole at the victim. The manual stresses your stance. Stand on a dry, non-conductive surface and ensure firm footing.
That footing part seems key. If you pull hard and your feet slip, you're going down.
And where you go down matters.
Yeah.
That leads to maybe the most crucial detail in the whole manual, the approach vector.
Okay.
It says, approach from the side, never from the front.
Break that down. Why does the angle matter so much?
It's physics. It's full zones. Imagine you're standing right in front of them, facing the cabinet. You hook on and pull. 2 bad things can happen. 1, your feet slip and you fall forward.
Right into the energized gear.
Yep.
Nightmare scenario.
Exactly. Or 2, the victim suddenly comes free, the hook slips, their shirt rips, and you fly backwards. But if you approach from the side, your pull is parallel to the equipment.
So if you fall past the danger zone, not into it.
You're engineering your own failure to be safe. You're managing your center of gravity relative to the lethal zone.
That is something you would never think of in a panic. Let's talk targeting. Where do you aim the hook?
The manual suggests clothing, a belt, or under an arm. The belt is usually the gold standard.
Why the belt?
It's central to the body's mass, it's usually sturdy, and it lets you drag the whole torso as one unit.
And there's a huge never warning in the text.
Never, ever hook the head or neck.
It seems obvious sitting here now, but in a crisis.
You have to resist that urge. Think about the force you're applying with a rigid pole. You could easily crush their trachea or damage their spine. You save them from the electricity only to kill them with the tool.
The manual uses the phrase smooth, controlled pull. That seems like an oxymoron when your adrenaline is just pumping.
It requires incredible mental discipline. You're not jerking them. It's a steady, increasing tension until you overcome the friction. You are dragging dead weight. It's a heavy, physical act.
And once they're clear, you've dragged them away. You want to rush in.
And the protocol says, stop. Lay them down gently, but do not touch them with your bare hands.
Why not? If they're away from the cabinet, the danger's over, right?
Not necessarily. There are concepts like step potential and touch potential. If there's a high voltage fault, the ground itself can be energized in ripples.
So even the floor might not be safe.
Correct. So you verify the area is clear, you make sure they're no longer conductive, then you begin first aid. It's just layer upon layer of caution.
It really is. It highlights that electricity is this invisible enemy. It doesn't bleed, it doesn't scream.
It just waits. It waits for one mistake.
Speaking of mistakes, let's go back to the tool itself. We know it's this rugged fiberglass lifeline, but the maintenance section of the ABM manual, I was surprised. This thing sounds, well, ironically fragile.
It is surprisingly delicate for what it is. We think of safety gear as indestructible, but the rescue hook has a kryptonite.
Or several, it seems like.
True. But the big ones are dirt, moisture, and UV light.
Okay, walk me through the dirt issue. Why is a dusty hook dangerous? Everything on a job site is dusty.
Because the hook's entire job is to be an insulator. But if you have a layer of conductive grime or oil or a mix of dirt and moisture on the surface...
You've created a path for the electricity.
Exactly. It's called tracking. The voltage can just travel along that dirty surface, bypass the insulation, and get right to your hand. A duty hook is a live wire waiting to happen.
So the inspection checklist isn't just paperwork.
No, it's applied physics. The manual mandates a visual check before every single shift. You're looking for cracks, sure, but mostly you're looking for contamination. Is it clean? Is it dry?
And the cleaning protocol really stood out to me. There's a very specific never pressure wash warning.
Chuckles, I know. That's going to frustrate a lot of people. On an industrial site, the pressure washer is the solution for everything.
But not for the rescue hook, why not?
Never. High-pressure water can actually damage the gel coat, that smooth outer layer of the fiberglass. It creates microscopic fissures you can't even see.
And those fissures trap moisture.
Exactly. It gets sucked into the core. Now your tool looks dry, but it's waterlogged on the inside.
Yeah.
You've just turned your insulator into a conductor.
That is such a critical detail. I can just see someone trying to be helpful, blasting it clean, and accidentally ruining it.
It happens. That's why the manual says mild soap, water, soft cloth. You have to treat it like a surgical instrument, not a shovel.
And the storage rules are just as strict.
No tossing in the back of the truck.
Yeah.
UV light breaks down the resin. Scratches and gouges compromise the insulation. ABM requires them on dedicated wall brackets in dry areas away from traffic.
They need to be protected until that one moment they're needed. Which brings us to our last piece. Locations.
Right.
None of this matters.
Yeah.
The physics, the technique, if you can't find the hook when the alarm is going off.
It's situational awareness.
Right.
You can't start looking for the fire extinguisher after the fire starts. You have to know where it is ahead of time.
So let's run through the ABM locations. If you're listening and you work on that site, picture this map. First up, main electrical room.
Next to the entrance door.
Why the door?
Think about the flow. You run into the danger, you grab it on the way. If you're already inside and need it, it's on your way out. It's on the egress path. You don't want to run past the hazard to get the tool.
That makes perfect sense. Where else?
The substation area, mounted on the north wall.
That specificity, north wall, is key, isn't it?
It saves you 5 seconds of looking around. In a crisis, 5 seconds is an eternity.
And the workshop?
In the tool cage.
Clearly marked.
And finally, the mobile units.
Right. Inside the emergency response vehicles. If you're working out on a line somewhere, that truck is your safety station. You need to know which compartment holds that hook.
So let's say the worst happens. The hook is used. You save someone. What do you do with the hook? Just hang it back on the wall.
Absolutely not. The manual is very clear on this. Any use of the hook is a major incident.
Who do you report it to?
Immediately. Site safety officer, project manager, HSE department. It triggers a full investigation.
And the tool itself. It's taken out of service. It's evidence, for one, but it's also been under extreme stress, both mechanical and potentially electrical. It has to be recertified or, more likely, destroyed. You never, ever just put a used hook back on the wall.
It just shows how serious this is. Using the hook means the system failed somewhere.
Exactly. The primary controls, the locks, the tags, the procedures, they've all been breached.
You know, as you wrap up, I'm just struck by the paradox of this tool. It is arguably the most critical piece of safety gear on the entire ABM site. It's the only thing that stands between a person and 50,000 volts, and yet it's the one tool everyone there hopes they never, ever have to touch.
That's the nature of emergency equipment, isn't it? It sits there silent day after day, but its value becomes infinite in that 1 second when everything goes wrong.
But the biggest takeaway for me, it's not even the hook, it's the procedure.
I agree completely. The hook is a marvel, but the real safety is in the software, not the hardware. It's that alert, assess, de-energize sequence. If you remember nothing else, remember that. The goal is to never have to reach for the hook in the first place.
So here's a thought to take with you. The next time you walk past an electrical room on site, or you're near a substation, find the hook. Don't just glance at it, really look at it, note its position, and ask yourself, if the person next to me froze up right now, locked in that tetany grip, am I mentally prepared to step back, assess, find that handle, and do what has to be done? Or would I freeze too?
It's a sobering question, but knowing the answer is what keeps everyone safe.
It's heavy stuff, but essential. Thanks for breaking this all down.
Stay safe out there.